It wasn't always a vacuum. It wasn't always a vacuum.
So yeah, Bill, I apologize. No new material today. We're going to be looking at homework problems, which may or may not interest you. But
No, stay.
I don't have audio for you.
It's okay.
Oh, the audio's, yeah, I think I know what the problem is. I don't think I know how to fix it, but I don't have audio for you. Apologize.
If you like sit here for long enough like this, you can feel your blood like pulsing through your fingertips, like lining each of the fingertips, because you gotta like sit and then hold it for a while.
I don't think you have to do this to do it. You just chill for long enough. I think you'll still feel it.
No, but this way you can feel it in the tips, against the tips. It's very like.
I know, but I can like still feel it in my tips. That's like this chill.
I can't do that. That's impressive. I feel with this finger, I feel the pulse of this finger. With this finger, I feel the pulse of this finger.
Are they in time?
Of course.
No, but your heart is slightly off center. Your heart is slightly off center, so you expect one to be a little before the other.
Don't talk about my heart.
My heart beat like 2 BPM.
That's pretty good. My friend who was a cyclist had a really low resting heart rate.
Oh.
A nurse commented on it once, and he wrote that night for a month. And he had one of those bicycle stands that you like lock your bike into, and you just in one place. And he would do that every day during the winter.
So I think what you need from me is not like a lot of details and calculations, but you need some perspective on like how to set things up.
Nice big picture.
Yeah, like some strategies for like when you see a similar problem on the exam or homework, then you'll know what to do. And oh, for sure. Let me do something just so I feel like I've done something, and then I'll take your question.
I almost emailed you a couple times for an example, but I kind of ended up not doing it.
Well, like by all means, email me with questions.
Yeah,
That's,
but it's just
you know.
like some of them take so much setup to like just ask the question, and sometimes writing it or doing it over Zoom doesn't feel like ideal.
You can do it. I believe in you. I believe in you.
Just like text a picture and send
I believe you can be concise.
This is another reason why we need to have Ken's phone number.
no, we need a Discord server.
Yeah.
So, I mean, yeah, I'll do that, whatever you want. If you want a Discord server, you can have one.
And you need to stream on Twitch.
Yeah, you gotta create.
I'll donate. We'll make sub icons.
Okay.
Can I suggest a title for today's class?
Yeah.
Ken's question pointer, but it's spelled K-E-N apostrophe S K-W-E-S-T-I-O-N K-O-R-N-E-R.
Oh, yeah, that's a, yeah, that's a hard no, sorry. Like, it's like, no. Okay.
Yes, you can.
Okay. This has devolved. Okay. 3.1.1. So consider the initial boundary value problem for the wave equation. On a bounded domain, recall this system models the small transverse deflections of a taut fixed string at 2 endpoints. So briefly, statement of this question was like UTT equals C squared UXX 3.1.1. X goes from 0 to pi and t bigger than 0. And you had initial condition u x 0 equals g of equals f of x. You had initial condition ut x 0 equals 0 on bounded spatial domain. Okay, and so verify that the set of functions satisfies PDE 3.9 and boundary conditions 3.10. So these were the product functions. U sub n equals cosine nct times sine in x. So these are functions that ultimately you get from the separation of variables procedure, but they're already given to you. And so verify they satisfy the PDE and the boundary conditions. So you're just taking 2 time derivatives and showing that's equal to c squared times 2 space derivatives. That's no problem. I don't think people had problem with that. And so you're verifying that it satisfies boundary conditions 3.10. So it doesn't satisfy these boundary conditions. It satisfies that the endpoints are fixed. So there was this supplemental boundary condition that u0t equals u pi t equals 0. So in space-time, you're going from like 0 to pi. And this boundary condition is on the vertical part. And like these boundary conditions are on this part. The boundary conditions on this part have no hope of being satisfied for the individual product function. But when you take the infinite sum of all of them, then you use like the Fourier series to try to get something equal to f. So part A is really just taking derivatives and showing that when you plug in 0 or pi, you will get 0. So that's no problem. So these are called fundamental nodes. They represent standing waves. Plot several time profiles for the fundamental node for n equals 2, c equals 1. Hit that with Desmos. Superimpose the part C, superimpose the fundamental modes by defining uxt, by defining this partial sum. So part C, if you're following along, n goes from 1 to infinity, I guess. It's not specified in the problem. Cosine nct sine nx. And determine the coefficients a sub n for which uxt satisfies the initial conditions 3.11. Initial conditions 3.11 were these. And so superimpose the solutions, add them together. You've got an infinite family of solutions, so you're adding them together now into an infinite series, and you're taking this linear combination, multiplying each one by a constant. So yes, that truly is a constant. And the question is to determine the constant that allows this to satisfy the boundary condition, the initial conditions here. And so yeah, like I was saying, the individual product solution has no hope of ux0 equals f, but it does have a hope of f of x equals ux0 equals a sub n, and then cosine in x, and goes from 1 to infinity. And if you want to just try to use the formula for the Fourier sine series, the problem that you have is that it's not like the formula for Fourier sine series would work if you were like on negative pi to pi, but you're not, you're on 0 to pi. So if you knew that f was an odd function, you could just like take the extension and then use the usual Fourier sine series formula. I guess you don't exactly know that, but anyway, it's not so bad. Just the linear algebra tells you always that a sub n is equal to take the inner product of f with sine in x. So you know that these sine functions are an orthogonal system. You divide by sine in x, sine in x, and you're done. You don't, I mean, you don't actually have to do this full calculation, right? So this one, the bottom part, is nothing but integral of sine squared in x from 0 to pi. And that's pi over 2. So you don't have to work out integrals like this all the time, you know? And I don't have that memorized. It's just that after like teaching the class for a while, you know, I just kind of remember it. Well, I don't have it memorized in the long term somehow, you know? Like when I teach my next class next semester, it goes out of my brain again or something like that. But I have it like short term memorized, medium term memorized. I don't know if psychologists study like a memory that's between like short and long term, but I feel like I have that for a lot of math information. So yeah, I think this is like 2 over pi times this, which is integral from 0 to pi of f sine in x dx, which actually is the formula that you would get if you assumed that f was an odd function, which would make this an even function, and then use like Fourier sine series, and then just go from 0 to pi and multiply by 2. But you weren't given that information, so whatever. I just used this linear algebra formula to find that formula for the coefficient, and then that solves part C. Part D, show that UXT solves the initial boundary value problem formally. Whenever somebody says show it formally, that just means you're not worrying about like convergence issues. So yeah, go ahead and differentiate under the integral sign. And the idea, of course, is since this is a linear equation and since each UN solves it, then the sum will also solve it. This sum will also solve it. So like, for instance, I won't write out all the details, but like UXT equals this sum AN UN, right? So if you take UTT, differentiating term by term means that this is AN U sub N TT. And from your previous problem, you showed that this was equal to like AN times C squared UXX, which is like the same thing as AN times well, I guess it's U sub N XX U sub N, which solves the problem. So if it's true for each term, and since you can differentiate under the integral sign, it'll be true for the infinite sum. So that's the schematic of what you're going there for part D. Find a formal solution as above if the initial conditions are changed to UX0 equals 0 And u sub t x0 equals. So how can you do this? So let's look at,
So then cosine here with t in it, and sine, since what t is 0, u is 0.
well, what's so funny?
We're making fun of Devon.
Oh, don't make fun of each other. Make fun of each other. Well, so are the product solutions still valid? So you had product solution, in this case, u sub n equals cosine n ct times sine of nx. And so they satisfy this condition. And
Would you have to take the derivative of that?
but so here's the thing that I'm thinking, right? So this boundary condition doesn't change, right? And because this boundary condition doesn't change, then that product solution is still good, right? And if you plug in these things,
Different initial conditions change it though.
Well, I didn't want this part. I think, wouldn't this just change the A in the sum? The coefficient?
I got
well,
a
let's
different product solution.
let's see. So let's take u x t equals y of t g of x. And so these boundary conditions are saying that, well, first you have this g of 0 equals 0, and you have g of pi equals 0. So those things don't change, right? But you also have, you also have this ux0 equals 0, which you can't really apply to this product solution, right? Because if you do, then you'll just get y of 0 g of x equals 0. I guess you could take this to mean that y of 0 has to be 0. But then if you do that, because this, well, maybe that's not bad. Because what's the equation that you get here from separation of variables? You get y double prime times g equals c squared y times g double prime. So you get y double prime over c squared times y equals g double prime over g. Equals minus lambda. So maybe you get these two equations with two sets of boundary conditions, but like the equation for the space part is still g double prime equals minus lambda times g, with g of 0 equals g pi equals 0. And now you get the same thing. You get y double prime equals minus c squared times lambda times y with y of 0 equals 0. So that tells you that your y of n can't have a cosine term. Is that right? So it has to be like, you know, without the constant, it has to be like sine of and lambda is going to turn out to be n squared. Yeah, so that's the argument. It's this one that changes, right? Is that what you were saying? Yeah, because the space conditions don't change, and you've got one extra time condition. Because when you plug in t equals 0 to this, you're kind of out of hope, right? Because you've got this, you know, a sub n times sine of nx. Like you're not going to have that identically 0 without all these coefficients being 0, which is going to like ruin everything. So instead, you take this initial condition and put it on the time part, which gives you something like that, which gives you that instead. Then you take the time derivative and you'll get cosines and then a factor of NC, and then figure out the coefficient using linear algebra in the same way. So that I think I can leave you with, but I guess what I wanted to illustrate to you was I don't think it's right to just, you know, to just say, oh, like this is sine. I mean, it's true, but it's good to make some argument to show why that's the case. Yeah. I'm not singling anybody out. I'm just like, yeah, that's right, Bill. I missed checking the other initial condition in part A, or the earlier part. Bill says back when this was F and that was 0, I should have checked that for the other part. And you're right. Okay, your questions.
Is there any, like, visual understanding of the relationship between a dot product and an inner product? A dot product of vectors and an inner product of. Is there a relationship between those two concepts at all? Actually, it's probably the other question I want to ask.
Yeah, so the question is, what's the relationship between the dot product and an inner product? So the dot product in Rn, so on Rn, you've got the dot product, which says you take two vectors v and w, and their dot product is like, you know, vi, wi, like goes from one to n, and what is an inner product? So like an inner product on a vector space V is a rule, sort of like some function that takes two inputs and gives a number like as an output. So it takes two vector inputs And it satisfies like some number of properties, you know, like the inner product of V with itself is like bigger than or equal to 0, and VV inner product with V equals 0 if and only if V equals 0. It has to be symmetric. This is for a vector space with like a real vector space. So vector space where scalar multiplication is by a real number. And it has to be linear. So like AV plus WY has to be equal to AVY plus WY. And by symmetry, that'll mean that it's linear in both places. So for example, you could take V equal to Rn, and you could take VW to be the dot product. So the dot product is an example of an inner product. So if you're a mathematician, then probably you work with dot product first, then over time, you realize that the properties of dot product that are important are really 1, 2, and 3. And you start to notice that other mathematical structures enjoy those similar results that really just came from these facts and not from the fact that it was the dot product specifically. And so in fact, it holds good that if you take V to be the vector space of L2 functions on A to B, so just these functions on the interval such that when you integrate them, when you integrate the square of it, then the answer is less than infinity. So certainly every continuous function is in L2, but there are discontinuous functions that are also in L2. So this is a vector space, and the inner product given by the pairing of Fg is integral from A to B of F times G. Amazingly enough, it does satisfy these 3 properties. With the caveat that inner product of V with itself, like this being 0, doesn't necessarily mean that F is equal to 0. There could be like a finite set of points or a set of measure 0 where F is non-zero, but that doesn't ever produce a problem. So for practical purposes, these 3 are satisfied, and that comes legitimate inner product. So it's kind of amazing that this formula has the same structure as this formula, at least in regards to these 3 things. And the fact that that structure exists makes this particular vector space important. Okay. Will, what was your question?
Well, while we're on the topic of like the link between vectors and functions,
Yeah.
I had a question about Gram-Schmidt orthogonalization.
Yeah.
It's pretty straightforward to understand it in terms of vectors, because that's just like making orthogonal basis vectors for that span of space. You take one vector and then you just subtract however much that vector is pointing in the second vector.
Yeah. Yeah.
But like when you're doing that for functions,
Yeah, so the question is like on conceptualizing the Gram-Schmidt process for like this vector space with that inner product.
Question where that
And
comes up is,
yeah, I know, I'm there. The question where it comes up is question 3.2.8, so deriving the Legendre polynomials. So it's a cool question. You start with this basis, 1x, or sorry, this set, 1x, x squared, x cubed, and take a equals -1, b equals 1. These are certainly L2 functions on that interval. And these are not necessarily orthogonal with respect to this inner product, are they? Right. And so Gram-Schmidt process will allow you to start with, you know, like the span of 4 vectors, and then from that construct a basis for the span. Yeah, such that, so Gram-Schmidt process will allow you to construct F1, F2, F3, F4, like with that property, right? So in terms of visualizing it, I don't know that there's a good visualization. I mean, I'm sure there probably is, but I don't know that there's a good visualization of this inner product. But the thing about the Gram-Schmidt algorithm is we often use visual crutches in linear algebra, but they're not necessary, right? And so the Gram-Schmidt algorithm says, well, you know, like start with just F1 equals 1. And like you say, to find F2, you maybe start with X and then subtract off the part that is parallel to 1, but like parallel with respect to that inner product. So in other words, you just use this formula that's given, although their notation was sort of exactly backwards from mine. That they call this F1, that F2, that F3, that F4, and then they want to take Gram-Schmidt to give you G1, G2, G3, G4, and so I would take G1 equals 1, and then what does it say? G2 is like F2, and then you subtract off the F2, G1 divided by G1. Yeah. So this is now, you're just taking X and you're subtracting off the part of vector X that's parallel to G1. I mean, this is the formula for like the coefficient in front of, you know, in front of G1, right? And so this gives you like,
Why don't you multiply that by G1? The ratio of the inner product?
oh, sorry, yeah. I even said it, right? That's the coefficient times G1. Just didn't write it. And so it's just X minus the integral from -1 to 1 of X times 1 divided by inner product of G1 with itself. So this is just what, like 2? So 1 squared from -1 to 1. When you say isn't that 0, did you mean this?
Oh, no, I mean,
Oh, you're asking isn't this 0? Oh, yeah, it is. That's fine. But I'm just describing the process, because that's what you asked about. Yeah. And then so on and so forth with G3 and G4. Yeah, give it a shot. There's lots of ways to define Legendre polynomials, so I think it's kind of cool that they come from Gram-Schmidt. And this tells you that Legendre polynomials are like automatically an L2 orthogonal system. So G3, how do we do this from linear algebra, right? So we've got G1 and G2. So G3 should probably be F3, but then subtract away the part on G1 and G2. Does that make sense? So I would do like F3 G2 over G2, G2. So I want to, given F3, I want to construct a vector G3 that is now orthogonal to both G1 and G2. So as long as these vectors are independent, then F3 is not going to be in the span of 1 in X. So I can actually subtract off the projection. This is the projection of F3 onto G2 minus the projection of F3 onto G1. Should give me G3. So that, does that scan? That sounds reasonable. And so I just sort of plug in. So this is X squared minus that mess. And this one is, well, I don't know. Okay, we'll just write everything out. So first of all, what's G2? G2 is minus 1, 1 of X dx, which is like X squared over 2 from minus 1 to 1, which is like 1/2 minus 1/2 equals 0. So what's the problem? Oh, squared. Squared. Thank you. So this has to be X cubed over 3 from minus 1 to 1, which has to be 2/3. So I'll just call this 2/3. And we already knew that G1 was equal to 2, right? So if those are correct, if I didn't make a mistake, then we'll proceed onward. So F3 G2 is now X squared times X, which is X cubed dx, which is now X to the 4th over 4 minus 1 to 1. So this one really is 0, right? Because it's odd function. And so this actually just totally goes away. And then we have F3 G1. Yeah, F3 is X squared and G1 is 1. which I just did, right? So this is x cubed over 3, giving us 2/3. So unless I made a mistake, which is totally possible, this is x squared minus f3g1, which is 2/3, divided by g1, which is multiplication by 1/2 times g1, which is 1. So x squared minus 1/3. Is that what all of you got? Like when you looked at it? And so these would be, I guess, again, in the problem's notation, this is P0, P1, P2, and you've got one more to calculate, which I'll skip. And for part B, find the best approximation of e to the x on -1, 1. Best approximation of e to the x with respect to these Legendre polynomials. So you're doing, you're approximating e to the x by C0, P0 plus C1, P1 plus C2, P2 plus C3, P3. So what you're doing is you're taking the projection of e to the x onto the span of P0, P1, P2, P3. And when you do that, the formula for the coefficients is just the usual Fourier formula. It's the linear algebra formula. So C n should be equal to e to the x inner product with Pn divided by its norm squared. So you just calculate this, like whatever it is. Sort of schematically write it down, but you've got formulas for P0, P1, P2. You will have a formula for P3. And so then you can figure out these coefficients and then you just put them in and you've got this nice Legendre polynomial expansion for e to the x. E to the x, thank you. So in the same way that you could expand out e to the x in like the usual Taylor expansion, you can also just do like linear algebra and say with respect to this L2 inner product, here's an orthogonal set of polynomials, so let's expand it that way. And if you complete this, you know, x to the n, x to the n plus 1, you take this countably infinite set, then you would then get a countably infinite collection of Legendre polynomials. And presumably you could then write that e to the x is equal to the sum, like Cn times Pn, with Cn's given by that formula. So it's like an analog for Taylor polynomials, which is kind of nice, except instead of using calculus for best fit, you're using the inner product, the linear algebra to give you the best fit. Well, it involves integration through the definition of the norm, but I think it's pretty clear what I meant. Okay, so only 2 minutes left. Is there enough time for me to ramble about like one problem really quickly? Yeah, I know you're trying to. Just go ahead and start playing that Oscars music. It's fine. I just want to make a really quick point about problem 3, 3.3.3, which said, look at f of x equals x squared on some interval from negative pi to pi. And you were to find the Fourier cosine series of this. I think. We'll find the Fourier series, and since it's an even function, you know it'll just be the cosine series, and you've got the usual formula for the Fourier coefficients there, and I won't go through that, but sketch the graph of the function defined on all of R to which the Fourier series converges. So your original function was just defined on negative pi to pi. Your Fourier series is defined on all of R. So what should this converge to? It's got to be the periodic extension of this, right? Because if this thing converges on this interval and it's periodic, then pi, 2 pi, 3 pi, then you look what happens. So I just think it's important to me to point this out. That's the function that you get convergence to. And what kind of convergence do you get? Well, you have these convergence theorems that says if you have continuous function, which this is, and if the derivatives are like piecewise continuous, then it'll converge pointwise and uniformly. So in other words, since there's no breaks here, you're not worried about hitting an average. This cosine series that you actually figure out legitimately converges to this thing, and then you restrict it to this interval to get, to get the thing that you actually wanted to begin with. So I think that's kind of nice. And what we might talk about a little bit more next time is why we care about those convergence theorems for Fourier series. But what I want to do, lots of integrals needed for Logan 3.2, number 8c. Yeah. Okay. So Bill's saying he used Maple to do 3.2.8, which sounds good. But yeah. So next time maybe some convergence theorems. Any question you ask about any homework problem, email it to me in advance. Otherwise, I'll just start doing some problems from Sturm-Liouville section 4.2 to give you a heads up on what you'll be seeing like on the next homework. So more problem day tomorrow. You have a chance to change the future by suggesting problems to me. Otherwise, I'm just going to ramble about whatever I want.
Have you posted?
So I haven't posted new homework yet on purpose. We're just taking a couple of days to relax and go over something. Our next scheduled test is 2 weeks from Friday on November 6th. I know, and I think I'd like to keep it there, unless there's strong opinions from the class to move it up or something like that. But I think November 6th is a good time to do that. Okay, thank you everybody for your time and attention, and I will see you later.